In this question, we're told that a car is travelling along a straight horizontal road. It starts from rest at point A and accelerates uniformly at a meters per second squared, reaching a speed of 18 meters per second. The car then travels at a constant speed for t seconds. Finally, the car begins to decelerate uniformly at zero point 0.7 meters per second squared, coming to rest at point B. A wants us to sketch a speed time graph to show the motion of the car from A to B. And I would want to somehow represent all the information that's been given. Diagram's a perfect way to do this. So just starting with the two axes, the horizontal is for time, the vertical is for velocity. We know we started with some acceleration, then some constant velocity, and then some deceleration. We know that the speed we got up to, the velocity we got up to, was 18. And here I'm just going to show that there are three parts to this journey: the acceleration, the constant velocity, and the deceleration. The time for which there was constant velocity, we're just told that that interval of time is called t. So that's all the information that we have, enough to put onto a diagram now. That's enough for the sketch. We will likely update this as we make our way through the question. In part B, we're asked to determine the time for which the car decelerates. Well, we're told that its deceleration is 0.75. Let's make use of that. We'll collect some Suvac variables. The original or the initial velocity for the deceleration period is 18. The final velocity is 0. And be really careful here. The acceleration, negative 0.75. There were no negatives in the text of the question, but they've told you it's deceleration, and there's an expectation that you will model that as negative acceleration. And we're looking for time. Let's go with the formula V equals U plus AT. Substituting the values we're working with, 0 equals 18 minus 0.75 t. Rearrange and we get t equals 18 divided by 0.75. The time is 24. 24 seconds of deceleration. So now we can add 24 to the diagram. We're also told in the lead up to part C that the car accelerates for 1/4 t. We can add that to the diagram. And the distance from A to B is 1,512. The question then specifies that we should calculate the value of t, that unknown time period of constant velocity, and the value A, the acceleration at the beginning of the journey. So we're going to make use of the 1,512. We know that distance on a velocity time graph is represented by the area. 1,512 equals half times A plus B multiplied by the perpendicular distance between them, the height. In this case, it's a half multiplied by t, which is going to be the short parallel side, plus 5/4t plus 24. That's going to be multiplied by 18. On these next few lines, I'm simplifying. 18 times a half is 9. We can divide by 9, subtract 24, divide by 9/4, and eventually we get t equals 64. The time where there was constant velocity, 24 seconds. Now let's find the acceleration. We'll collect Suvac variables for the initial part of the journey. Initial velocity of 0, final velocity of 18. We're looking for the acceleration. And here's an important point. We know that the time is 1/4 of t. Well, if t was 64 seconds, 1/4 of 64 is our 16. 16 seconds, that's how long the car was accelerating for. Let's put this into the formula. V equals U plus AT. Substituting in the values that we're going to work with. Acceleration is 18 divided by 16. 1.125 meters per second squared. Part D of the question asks us to sketch an acceleration time graph to show the motion of the car from A to B. Well, we already know there are three parts of the journey: the acceleration, the constant velocity, the deceleration, or acceleration, zero acceleration, deceleration. I'm going to reproduce my velocity time graph over here just so you can see exactly where these accelerations are coming from. Initially, the acceleration which we just found was 1.125. So it's a little bit more than 1. So acceleration here, 1.125. Then constant velocity means 0 acceleration. So in between these 2 points, there's 0 acceleration. And then it's decelerating afterwards, and decelerating at a rate of negative 0.75. All of these are now shown, and this is our acceleration time graph.